this exercise. We will tackle a nodal analysis for this particular circuit that's in your textbook, and that was example 8-14. Okay, so this was the initial circuit. The question for this circuit was, what is VAB? And so what we can see here is that we have two current sources, one voltage source, and we have to see if we could make sure that maybe the equivalent circuit is consistent in terms of sources. So we'll have to look at the equivalent source that will achieve that goal. We could look at this circuit right here as a current source in itself. We can convert it into a current source. So the equivalent of that with the whole circuit will be something like this. So the whole circuit will be equivalent to, so here's our I, 1, so that remains there. This remains right here, and this would be I2, except at point A, we will have a current source, and this will be I3 plus a parallel resistor R3 let's not forget the resistor here for this one. That would be R1. And finally, this will have its own parallel internal resistance. And that would be R2. Okay, so this will remain point A. Okay, now if A was here and B was here, and they're looking for VAB, that is not B. This point is not B. Okay? So we can call this point maybe all of this C. So this point here could be C. So you'll have C here. As a matter of fact, to solve this circuit, it's probably a good idea to use all of this as a reference. So we'll put a ground here for now. We will see a technique that we're going to use between the nodes here and the ground in terms of voltages to come up with our equations. That would be the strategy, by the way. At this point, notice I have two nodes here. Now we can do a current node for these and see what they might be. Now, the key here is to go ahead and arbitrarily set up some current directions for any of these branches that have resistors for now. If the values happen to be negative, that's not a problem. That means the direction was the other way. So let's assume that I1 right here that goes, or IR1 that goes through R1 is this way. And let's consider this one IR3. Okay. Now remember, this is an index, not necessarily, and let's assume this one is IR2. Okay? So now we can go to each one of these and try to figure out, okay, so what is the current going in what are the currents going into any of these nodes and coming out of the nodes? And then we could do a current loop based on that. So this one here, these are going to be constants. So I am going to put their values here. So this would be the 200 milliamp. This would be a 50 milliamp. So we'll leave those here. And this one, I3, we could configure that since we did the equivalency right here, is going to be equal to E that we have here divided by this internal resistance. So that would be E divided by R3, which will be equal to 6 divided by 30. So that would be a 0.2, which is 200 milliamp. So that gives us 0.2 amp, which is really 200 milliamp if we want to keep everything in milliamps. So this would be a 200 milliamp right here. Okay, so let's look at this node right here. Let's call it 1. Let's call it A, and let's call this one B. Big A and big B. Okay, so for big A, so big A right here, we have the currents I1. So visually speaking, we have I1 going in like this, which is your 200 milliamp. You have your IR1 going out, and you have I2 going in. And don't forget, you have IR2 going out. Okay, so let's make the, so this is our node. So yeah, so let's make the equality. So whoever is going out will be on, let's say, the right-hand side, and whatever is going in will be on the left side. So we could do something like this. I1 plus I2 equals IR2 plus IR1. Okay? Next, let's look at node B. And again, pay attention to the direction of the currents. So we have I3 going in. Here's the node. You have IR2 going in. You have IR3 coming out. And you have I2 coming out. So same thing. This time, let's go ahead and do the going in on this side. So IR2 plus I2 equals, what is that? Plus I3, not I2, equals I2 plus IR3. Okay, so now we have some sort of a sense of the current Kirchhoff law going on at each one of these nodes. So to solve for this problem, however, we are going to look for the voltages, let's say, at this point relative to this reference. And let's call this side here, so anything here from here to here would be V1, and anything from here to here will be V2. Okay, so we could tell that V1 itself will be equal to IR1 times R1. And we could also tell that V2, right, will be IR3 times R3. Okay, so we could replace these currents, IR1 and IR3, by these two voltages. Okay, so we could look at IR1 equals to V1 divided by R1, and we could see that IR3 will be equal to V2 divided by R3. Okay, what else? How about the difference between V1 and V1 and V2? Well, that defines IR2. So we have these. Let me just put box here. And let's write down here the difference between these two. So VA or V2, let's see. So if we have a source, V2 minus V1, right? So if the current is going in this direction, we will do V1 minus V2. So if it comes out negative, that's not a problem. Let me just erase here and make sure that we do this correctly. The voltage is going to be pointing this way. So that would be V1 minus V2 equals IR2 times R2. Can we deduce what IR2 is? Sure. IR2 will be equal to V1 minus V2 and the whole thing divided by R2. So these are going to be key to what we're going to do here and here. Okay? So now we know these are constants, so we're going to move them to the right-hand side. So let's say we have IR2, so let's go ahead and do for IR2 here. So for A, again, we have IR2, which is V1 minus V2 over R2, plus IR1, which is V1 over R1, equals to I1 plus I2. Now, I1 is 200 milliamp. I2 is 50 milliamp. So we could simply say 250 for now. Okay. Can we rearrange this so we can have V1 on one end, V2 on the other? And the answer is yes. You know that this equation here will be V1 over R2 minus V2 over R2 plus V1 over R1 equals 250. So we can rearrange this where V1 now will be equal, if you factor in V1, will be 1 over R2 plus 1 over R1 minus V2 equals 250. Excellent. Let's do this for B now. Okay, so for B, this time I'm going to have IR2 minus IR3 equals I2 minus I3. Okay, we have IR2, which is V2, or V1, I'm sorry, minus V2 over R2 minus IR3, which is V2 over R3. And we have I2 is 50 minus 200. So that would be minus 150. Okay, so now we could pull out V1 over R2 minus V2 over R2 minus V2 over R3 equals to minus 150. Okay, can we do the system of equations right here for this? And sure enough, so if we pull out this one right here, so let's go ahead and do it here. So that's V1, 1 over R2 plus 1 over R1 minus V2 equals 250. How about V1 over here? So V1 times 1 over R2 and factor in minus V2 of 1 over R2 plus 1 over R3 equals to minus 150. Do we have a system of equation? Yes, we do. Can we solve this as a matrix? Yes. You could do this. So you would have 1 over R2 plus 1 over R1 minus 1. And then you would have 1 over R2. I'm trying to see if I made a mistake. Yes, I did. This would be R2. So that would be R2. And that would be over R2. Good thing I caught it. Minus 1 over R2 plus 1 over R3. That would be V1, V2, $250, and minus 150. And that's how you would solve for V1 and V2. Now, once you have V2, for example, okay, remember that V2 now, V2 is the voltage from A to C. So V2 will be equivalent to all of this. So that would be VAC will be equal to V2. Okay, well, what else V2 is equal to? Well, V2 will be equal to E plus VAB. Excellent. Can we find VAB from that? Indeed. VAB will be equal to V2 minus E. And there you have it for your last solution.